Hello friend, welcome to ashatech.com. Today we want to talk about the rate of flow of a liquid or discharge and the continuity equation. Rate of flow of a liquid is defined as the quantity or the amount of a liquid flowing per second through a given section of a pipe or channel. It is generally denoted by Q. So considering a liquid flowing through a pipe, let A be the area of cross-section of the pipe, V to be the average velocity of the liquid. Then discharge Q will equal to area times the average velocity. Now, if this area being talked about here in this definition is in square meters and the velocity is in meters per second, then Q will be in cubic meter per second, or what we can call cumex. So wherever you meet the word cumex and they are talking about discharge, just know they are meaning the amount of flow in cubic meter per second. Discharge can also be given. Discharge can be in can be in liters per second, can be in liters per hour, it can be in liters per minute, it can just be in any units of volume, just units of volume per unit time. So whichever units you have here for volume over time, then this one will be discharge, or will always give you the rate of, or will give you rate of flow of a fluid. Having understood what discharge means or the rate of flow means, let us now discuss the continuity equation. The continuity equation is based on the principle of conservation of mass, which states that if no fluid is added or removed from the pipe in any length or any section, then the mass passing through the different sections is the same. That is the principle of conservation of mass for these fluids that are flowing. Considering now two sections of a pipe, 1, and 2, let area A1, to be the area of the pipe at section 1, V1 to be the average velocity of the liquid at section 1, and low 1 to be the density of the fluid at section 1. Then A2, V2, and low 2 to be the corresponding values at section 2 being considered. Looking at our diagram here, looking at this diagram, it is showing part of a pipe that is diverging. Okay, this pipe was continuous, but it is diverging in that way. Now, if this is section 1, then this is A1, which is the area of cross-section here, V1 to be the velocity, average velocity of the fluid flowing in here, and low 1 to be the density of the fluid here. A2 is the cross-section of area at the section 2, V2 to be the average velocity at section 2-2, and rho 2 the density of the fluid at that section. Therefore, total quantity of a flowing fluid through section 1 per second gives you the density of the fluid times A1 times V1. This is simply coming from the fact that the quantity of the fluid, that is in terms of mass, it is mass of the fluid over time. But remember, mass M is equal to density times volume. Now, if it is mass per unit time, then it will be over time. Meaning that since also volume, this is volume, please. Since this is volume, then volume per unit time can be from just having area times velocity. So when you look at the units for volume per unit time, and the units of area times velocity, it will still give you discharge, which will be volume per unit time. And therefore, bringing it in here, your mass per unit time would give you density times area times velocity, and this would now bring you to this. So if it is giving these quantities or characteristics at section 1-1, then it will become at 1-1, it will give you rho 1, A1, and V1. Likewise, at section 2-2, it will give you rho 2, A2, and V2. Having understood that, let us recall the law of conservation of matter or mass, that the mass per unit time through section 1-1 is equal to the mass per unit time through section 2-2. In other words, if I consider it to be m dot to be mass per unit time at 1-1, it will equal to mass per unit time at section 2-2. It means therefore that if this one was equation 1 and this one equation 2, it would give you from 1 and 2 rho 1 V1 A1 will equal to rho 2 V2 A2. This equation is the one we call the continuity equation, and it is applicable to both compressible and incompressible fluids. And that's it. If we now take assumptions that this flow is steady and incompressible, then for incompressible fluids, if the fluids we have considered them to be incompressible, then it means rho 1 is equal to rho 2. In other words, they have a constant density. Any incompressible fluid has got a constant density, meaning it is not easy to compress, and so its density is constant throughout. It doesn't change. And therefore, from this equation, if this is equation 3, it means from equation 3, put rho 1 equal to rho 2. If we put rho 1 equal to rho 2, then equation 3 becomes rho 1 V1 A1 equal to rho 1 V2 A2. Now, if this and that will go, they will go. Let us kill them and make 1 here. It means V1 A1 will equal to V2 A2. This is a continuity equation. Therefore, A1 V1 is equal to A2 V2 is a continuity equation. With the following assumptions in mind. Assumptions taken here. Assumptions taken are: 1 is that the flow is incompressible. And 2, that flow is steady. Thank you so much. Follow us in our next lectures.